Hello boys and girls. So one way to describe what we are going to do in this video is we are establishing propositional logic consequences of Bayes' theorem. I have made a video 4 days ago on Bayes' theorem where I commented from a much more practical side. There's a small Python script if you want to do some practical calculations. I give some examples. I give you a Python script to do some plots to understand how to use Bayes' theorem. In this video, this is what I actually wanted to get at. This is one of those more logical minded videos. I'm going to scroll up here. There is the this rule, Bayes rule, you multiply certain things. One of those entities that you multiply is the conditional probability P of B given A, right? There is a sense in which this is a generalization of the probability for B. You have an extra assumption. And at the same time, already the way I say it, the probability of B given A is a sort of implication, right? So in particular, when I say the conditional probability of B given A is 1, like 100% certainty that B holds when A holds, this is akin to the logical implication A implies B, right? A implies B, where A and B are certain propositions, is a proposition, and the equality to 1 is a proposition. And the other extreme, there's no chance that B holds when A holds, is the negation of this implication in this reading. So the conditional probability acts as a probability for this implication proposition. This is one way of reading it. In this video, we are juggling basically two notions, the probabilistic notion and the propositional logic notion. And here, when I talk about conditional probabilities, I'm not even talking about a certain foundation that gives rise to a certain definition of the conditional probability. There's a way of looking at the rules and Bayes' rule as an axiom, and we are going to see what follows from that. Much of the video will be set theoretical, or rather measure theoretical, so that we have something to work with and can be even more sharper about it. But I just want to emphasize that I'm juggling two frameworks here, and I don't choose like a meta-theoretical framework to prove many formal equivalences. There's just some sharp parallels, and in this sense we speak of implications. Okay, so clearly or surely here as I write, the probability for this proposition, not A or B, right? This should not be smaller than the probability for just B holding, right? So this is a disjunction, B holds or something else holds. It should be easier to come by. It should be more likely or maybe equally likely as just P of B. And, this disjunction implies this implication, and classically also the other way around. And so there we have a relation between the implication from A to B and just the probability of B. And there's then a sense in which Bayes' rule here, as I've written it down here, is making this relation much more explicit. It says that this implication from A to B equals the probability of B and then a certain factor. This is this factor here. And this quantifies what this relationship is here. And I will write down several ways Bayes' rule in this video. Here are two, right? So here in the denominator you have the so-called marginal probability for A, and in case you have a partition over a hypothesis space, meaning all the different possibilities, then you can write this here as a sum. This is a sort of expectation in the second variable here. So this is just another way of writing Bayes' theorem. This is then the factor that quantifies this relation. And at the same time, Bayes' rule relates this implication from A to B to the implication from B to A, right? So there's also this relation with this very simple ratio depending on A and B. And we are going in this video see some hard propositional logic theorems that mirror this and that are also in a certain sense implied by Bayes' theorem. And again, I want to emphasize that this is not a strict generalization with our set theoretic framework, because it's not the case that we can make we just derive propositional logic from that in a generalized sense, because there are certain exceptions we have to take. And going to that, now is the phase where I narrow down a little bit what I mean by conditional probability. There's like one model the main model I'm going to work with, this probabilistic Kolmogorov axiom sort of framework. I have a measure space, call it T, and the probability measure is now a function of subsets of this T. Of course, there is this very strong relation between predicates and sets, and in this way we can still sort of think of this as a sort of logical thing, like the probability of 3 out of 7 coin flips being heads can then be modeled as a certain subsets of the sequence space with 7 entries, or all of the sequences where, what did I say, 5 out of 7 entries are heads and not tails, and so on and so forth. So there's the set predicate correspondence, and in this sense we are while here above with the probability for some implication, this is still sort of mirrors this. But here now I'm just dropping into this like fully formal set theoretical framework, if you want. Okay, so here the conditional probability is then defined in terms of other things. I have this measure, and I speak of an intersection. And one thing I really want to highlight is that here to have this implication, this conditional probability B given A makes sense, I presume that I can actually divide by this number, meaning that this number is not 0, or in other words, A is not a measure 0 set. For example, that is not the empty set. And so whenever I have a relation and I write P given A, the conditional probability there, then I've already presumed that A is not false, right? So this will be a limiting factor for a bunch of derivations that I always have to say, except for this case where the assumption is actually known to be false. My credence is 0. This holds. And in particular, if I have the implication from A to B, A implies B, then the case where A is false is the explosive case. So this explosive case will sort of be ruled out up front in all my sort of derivations using the conditional probability as a generalization of the implication. Okay, so in the set theoretic framework, right, I can multiply here by P of B in form of a unit, and then I have another way of writing this relation that I had above, with the marginal probability and with the expectation value. Here we see that the implication from A to B becomes this sort of very symmetric factor. Several ways of looking at the Bayes theorem here. Okay, so before we get into conditional probability here, we have sort of a warm-up session where I will also point out something sort of sweet, and we will see how this sort of generalization come into play. So, you have the disjunctive syllogism, you do the contrapositive, and then you derive this theorem. The negation of the implication is equivalent to the conjunction of A or not B, or here, like more formally, if I don't use excluded middle, then not A. It's even read in this direction a little bit stronger. You can, for the sake of this video, just remove the double negations. I just like to prove my theorems like that since a few years, because you see a little bit more of the computational content. But this is, for intents and purposes, A and not B. And in particular, for the connective of implication, this is one of the connectives that is special in the sense that there is exactly only one case in the equivalent semantics, right? If you write down the truth table for the implication A to B, this is like a connective between two propositions. Propositions, if you say there can be true or false, truth value true, truth value false, then there's 4 combinations. And there's exactly one way in which the implication can fail, and this is if A holds but B does not hold. This is the one situation where the implication fails. And Now, we can take the law of total probability, right? So we have the hypothesis space is like just two possibilities, hypothesis Q or hypothesis not Q, and the law of total probability here reads this sum of the probabilities is 1, right? This sort of reflects the law of exploding middle. And then plugging in what we have just derived above, we have exactly the probability for this implication. And this thing we're going to read as like conditional probability is exactly 1 minus, and then in this truth value reading, this exactly one other scenario, right? Where A holds and B does not hold. So there's a sort of clarity to this sort of this probability, this probability expression, this conditional probability, if you want to identify this with the probability for the implication, then we can also express it as just 1 minus and then this conjunction scenario. I just want to give this up front because this has a certain like very hands-on reading in that sense that conjunctions are a little bit easier to deal with usually than implications. Okay, so this is just a warm-up comment, but now we're going to get into some derivations and implications of the Kolmogorov framework. So firstly, we look at some extremal cases. If the implication that we want to look at is the total space, the total measure space T, then just applying set theoretic laws, the intersection of T and A is just A, and so we find that this implication is 1, and like this probability is 1, and this happens to be exactly also the value of P on T. And so this sort of clearly mirrors this propositional logic theorem that we have here, right? So that A implies T, the whole space, or the trivially true proposition is true and is basically the same as just the likelihood for T. So in other words, this trivial conclusion is just true whatever you do. No matter what you plug in for A here, it's always the same value, just P of T. And we have this first sort of easy to buy mirroring, right? The implication of the triviality is also just this triviality. And again, I want to emphasize that here we have this sort of generalization, but not a full generalization, because if I talk about this implication, I've ruled out the explosive case where A is actually false. So while this holds also where A false, here I cannot really speak about it. Okay, then going on, and we will generalize this in a second. Here we have the trivial assumption, P given the trivial assumption, and then we do set theoretic calculus and we find this is also just P of B. So here the trivial assumption actually does not help us at all, right? So trivial assumption implying anything is just as good as the conclusion itself, right? And here this is also, again, it's a nice generalization because it does not just hold for the value of B being exactly 1. In this sense, it's a generalization. In this sense, it's actually also a full generalization in the sense that the denominator is here and never 1. Okay, now these were some easy cases. Now we're going to get in a little bit more tricky math. If I look at the inclusion-exclusion principle, I can toy around, like shift the left and right a little bit, identify some certain delta here, which is this probability for this union minus this expression here. You just follow it on screen. And now if I impose that the probability for P for Y is 1, like either that Y is actually T or some other full measure set, then by monotonicity of the measure, Y and some other set will also be 1, and so the delta is actually 0. And so I find that this intersection here in the case that P of Y is 1 is just P of X. And here I can read off two theorems depending on what I plug in for X and Y. On the one hand, if I say X equals A, then I have that the probability for A being 1, I have this result. This is literally a generalization of what we just had here. except I don't use just t equals a, but I sort of generalize it to an a which has the full measure of the space. And there are some more like non-elegant examples where this might hold, where a is not, like you take a singular point out and the measure doesn't change, but it's not actually full t, so on and so forth. But we can also choose for y to be a, and in this case we can divide by p of x, and then we get this rule out. So if a is 1 is certain, then again the probability that this is implied, the trivial conclusion, does also hold, right? So this is like, it is sort of sensible, right? If the conclusion is true, trivial, like similar to this, these arguments that we had above, then this implication also does hold. These are sort of nice generalization wherever this conditional probability is defined. And here I write down how to read this, where the credence of something established to be true is not lowered by adding some further assumptions. And this, if I read the conditional probability as an implication, mirrors exactly the implication introduction law in this propositional form, right? A holding implies that anything implies A. Okay, and further, also in the set theoretical approach, I already had the situation above where I compared law of x to the middle to the law of total probability, where the hypothesis space is just these two propositions, Q and not Q, or whatever it was. And now also with sets and complements, I can mirror this. And then we are, just some set theoretical operations. I can also generalize this to this theorem, which then mirrors this formally generalized excluded middle statement. It is not actually more powerful in the classical calculus, but you can see how this is a mirror of that. Okay, so finally we go on to the more interesting examples, I would say. Again, Bayes' theorem looks like so. Now, let's say both of the these function values on the left hand side are 1, right? We have in classical analysis, if the product of two numbers are 1, and these numbers are not just in R but actually probabilities between 0 and 1, then it means that I wrote element R, but of course it must be a value of the probability. Then this means that both of these factors on the right must also be 1, right? So this is one implication. And similarly, if the product of those is 0, then classically one of those must also be 0, right? I hope this is clear. And so from this follows, we said that probability of a proposition being 1 is the same as charging the proposition to hold. And from this we read off this relationship. If 100% B holds, 100% B implies A, this is this side, then just by arithmetic of analysis, we get that both of these must also hold. And so we have here this implication. And this is also indeed a theorem of propositional logic. This is, on the one hand, this means that if the left-hand side holds, then this implication holds. We already had the fact that B implies A implies B, the introduction law, implication introduction law. But now we also can read off here that if B holds and B implies A, then A holds. This is modus ponens. So this is also implied here by imposing these rules and the analysis calculus. And at the same time, the second law here says this is a little bit similar, but are also removed. If one of those are, my credence is literally 0, it's actually false, then this means the left-hand side must be false, and so one of those must also be false. So we have this relation. And indeed, I can take this relation, I can take the contrapositive, I take the classical inference rule where I pull the negation into the conjunction and flip the two propositions and get a disjunction out of it, and you can derive this. This is clear, sort of trivial to prove, and then once you have this, then classically you can also prove this. And this is also another way in which we now inferred this relation. And furthermore, what you can also read off here is that if P of B and P of A are the same, then what follows is that P of A given B equals P of B given A, right? So, and this corresponds then in the extremal case where the probabilities are 1 to this proposition here, right? B and A being equivalent obviously implies that this symmetric right-hand side is equivalent, but also you can also prove this very easily in the other side, basically with modus ponens. And now, apart from the case where the conditional probabilities are not defined at all, we have a generalization of this, because I divided out by P and B of A, but this I cannot just divide out when they are 1, but I just need to impose that these probabilities for B and A are the same, and then I get this result that the probabilities for the implications in both directions are also the same. So in that sense, it's a very nice generalization apart from the explosive case. Okay. And finally, we are already almost at the end. If you take the Bayes theorem and look at negations, right? So you plug in for not B but not B, and then you can translate the negation for the probability for the negation for 1 minus this probability. You divide by one of the factors, assuming that this sort of case is ruled out. You get this rule. Further, you also negate the conclusion. You get this rule, and this is also, I think, is a very nice formula. It basically tells you, like, after flipping from the propositions to negated propositions, how to compute this from these purely positive propositions, right? Here on the right-hand side, there's no negations. On the left-hand side, it's full of negations. And now again, assuming that this explosive case of false A is ruled out, we can actually now read off here the fact that if the left-hand side is 1, and this is all non-zero, then it follows that also this numerator must be 0, or in other words, that P of B given A must also be 0. And we can do the same reasoning the other way around. So we find that in these extremal cases, there is a correspondence. When the one is true, then the other is also true. And this clearly mirrors the contraposition law, right? So if you just, you can, just by my definitions of what I mean by the probability of something being 1 above, we have now derived this. And so you see how from certain analysis rules and the imposition of Bayes rule, good parts of propositional logic follow out. I wanted to establish the strength of these few rules in for basically seeing if you adopt these probabilistic laws, what propositional laws you can basically not deny anymore. And it is sort of fine-tuned, which is also interesting, right? You cannot just say, I get all the relations in the propositional calculus, but you have to make some concessions, at least if you use this measure theoretic reading of the conditional probability, where there you have a division and you don't want to divide by 0. And the last thing I want to say is that something it's a sort of a pet peeve that I always like to point out, is that I draw a distinction, and I would like for more people to do that, between Bayes rule and Bayes theorem, right? Because you can speak of conditional probabilities very easily, and you might impose almost as an axiom, like a Bayesian, the Bayes rule. And then you have this rule, and then you can do your calculations. But in that case, you have not chosen a framework in terms of which you have defined the conditional probability. If you write down conditional probability in terms of set theory, then you make you just look at where did we have it? 6 seconds. Yeah, you can look at by the definition of this object, and you have this very symmetric relation, and then you find out, Bayes theorem by easy symmetry argument holds. But then you have proven a theorem, which is called Bayes theorem, in the framework in which you have chosen to model the conditional probabilities. But you might not choose to take that particular foundation, or any foundation at all and can still impose base rule. And then I speak of rule, I like even intuitively I distinguish between rule and theorem, so I wanted to also highlight this at the end of the video. Okay, at 25 minutes, I think I was quick. I know I hasted through the video, but I'm glad. I think it turned out okay. So with this, take care. If you want to see more probability theory in this pure form, this is almost a little bit logical and philosophical. I can also do more. Otherwise, will go in with some future videos in a more applied direction again and computerize things, because this is all stuff in the context of efforts to talk about diffusion and this kind of things. Okay, I'm rambling now. I wish you a good evening.